Welcome back to the channel. Today, we're diving deep into one of the most crucial yet often overlooked aspects of training neural networks, learning rate scheduling. Have you ever wondered why your model trains perfectly for the first few epochs, then suddenly starts bouncing around like a ping pong ball? Or why it takes forever to reach that final 1% accuracy improvement? The answer often lies in how you schedule your learning rate. By the end of this video, you'll master 7 different learning rate scheduling techniques that can speed up your training by up to 40% and help you achieve better final accuracy. So, grab your coffee and let's optimize those gradients. Let's start with the fundamentals. Learning rate scheduling is the technique of systematically changing your learning rate during training rather than keeping it constant. Remember our basic gradient descent equation? Here, alpha is our learning rate. Traditionally, we keep this constant throughout training. But think about it. Does this make sense? Imagine you're hiking down a mountain in fog. At the beginning, when you're far from the bottom, you can take large steps. But as you get closer to the valley, you need smaller, more careful steps to avoid overshooting. This is exactly what learning rate scheduling does. We start with larger learning rates for quick initial progress, then gradually reduce them for fine-tuning and stability. There are 3 compelling reasons to use learning rate scheduling. First is faster convergence. With the right schedule, you can reach your target loss much faster than with a fixed learning rate. Second, better final performance. By reducing the learning rate as we approach the minimum, we can achieve better final accuracy and avoid overshooting. Third, training stability. Scheduled learning rates help prevent training instability, especially in the later epochs. In fact, almost every state-of-the-art model you've heard of, ResNet, BERT, GPT, they all use some form of learning rate scheduling. It's not optional, it's essential for competitive performance. Let's dive into our first scheduling technique, Step Decay, also known as stepwise scheduling. Step Decay reduces the learning rate by a fixed factor every few epochs. Think of it like taking the stairs instead of a ramp. Here's how it works. We start with learning rate 0.1. Every 30 epochs, we multiply by 0.1. So epoch 0 to 29, LR equals 0.1. Epoch 30 to 59, LR equals 0.01. Epoch 60 to 89, LR equals 0.001, and so on. Pros: simple to implement, works well for many problems, predictable behavior. Cons: aggressive drops can be too sudden, requires tuning of step size and decay factor. Next up is Exponential Decay, the smooth cousin of Step Decay. Instead of sudden drops, Exponential Decay smoothly reduces the learning rate after every epoch or even every batch. Notice how Exponential Decay provides a smoother transition compared to Step Decay. This can lead to more stable training, especially for sensitive models. A popular choice is to decay by 0.96 every 1,000 steps. This gives you a nice balance between initial speed and final precision. Now for one of my personal favorites, Cosine Annealing. This technique follows a cosine curve, creating a smooth, natural decay pattern. The beauty of cosine annealing is that it starts fast, slows down gradually, and then really fine-tunes at the end. What makes cosine annealing special is its gentle approach to the minimum. Unlike Step Decay's sudden drops, it provides a natural, smooth path that often leads to better final performance. In practice, cosine annealing often outperforms Step Decay on image classification tasks, especially when training for longer periods. Here's where things get really interesting. Cosine annealing with warm restarts, also known as SGDR. The idea is brilliant. Instead of continuously decreasing the learning rate, we periodically restart it to a higher value. This allows the model to escape local minima and explore different regions of the lost landscape. Think of it like giving your optimization a fresh start every few epochs, but with accumulated knowledge from previous cycles. T0 is the initial restart period, and T-mult determines how much longer each restart cycle becomes. The results can be impressive, often finding better solutions than traditional monotonic schedules. Linear warm-up is crucial when training large models or using large batch sizes. The idea is simple. Instead of starting with your target learning rate, you gradually increase it over the first few epochs. Why do we need this? When we start training, the model parameters are random, and the gradients can be very large and unstable. Starting with a high learning rate can cause the model to diverge immediately. Linear warm-up is essential for transformer models like BERT and GPT, where it's typically combined with other scheduling techniques. Now for something completely different, the one-cycle policy, popularized by Leslie Smith and FastAI. This technique increases the learning rate for the first half of training, then decreases it. It's counterintuitive, but incredibly effective. The complete cycle consists of a warm-up phase, a peak phase, and a annealing phase, all within a single training run. The results are often remarkable, achieving the same accuracy in significantly fewer epochs. Some teams report training times reduced by 5 to 10x. Why does this work? The high learning rate phase helps escape sharp minima, while the low learning rate phase ensures smooth convergence to flat, generalizable minima. Sometimes you don't want a predetermined schedule. You want to adapt based on how your model is actually performing. That's where reduce on plateau comes in. This technique monitors your validation loss, or any metric, and reduces the learning rate when improvement stagnates. The key parameter is patience. How many epochs to wait without improvement before reducing the learning rate. This approach is particularly useful when you're not sure how long your model needs to train or when training dynamics are unpredictable. It's also great for transfer learning scenarios where different layers might need different amounts of training. Exponential decay gives you fine control over how aggressively you want to reduce the learning rate. By adjusting the power parameter, you can create different decay patterns. Power of 1 gives linear decay. Higher powers create more aggressive decay toward the end. A power of 0.5 creates a gentle curve that's somewhere between linear and exponential decay. Now let's talk about practical implementation. Here are my top tips for successful learning rate scheduling. Tip 1. Start simple. Begin with step decay or exponential decay. They're easier to debug and tune. Tip 2. Monitor your metrics. Always plot your learning rate alongside your loss curves. This helps you understand what's happening. Tip 3. Combine techniques. Don't be afraid to combine linear warm-up with cosine or polynomial decay, or use reduce on plateau in conjunction with step decay or exponential decay. Tip 4. Different LR for different layers. For transfer learning, use different learning rates for different parts of your model. How do you choose the right schedule? Here's my decision framework. For computer vision, image classification, start with step decay or cosine annealing. Object detection, warm restarts often work well. Transfer learning, reduce on plateau with discriminative rates. For NLP, transformers, linear warm-up plus cosine or polynomial decay. RNNs, step decay or exponential decay. Fine-tuning, one-cycle policy can be very effective. For time series, reduce on plateau, it adapts to data characteristics. Exponential decay for stable patterns. Quick reference guide. Fast training, no netbox, one-cycle policy. Stable, predictable, step decay. Smooth, natural, cosine annealing. Adaptive, reduce on plateau. Large models, linear warm-up plus another schedule. Let me share the most common mistakes I see. Mistake 1. Too aggressive decay. Reducing learning rate too quickly can get you stuck in suboptimal solutions. Mistake 2. No warm-up for large models. Starting with high learning rates on large models often leads to immediate divergence. Mistake 3. Not monitoring the schedule. Always log and visualize your learning rate schedule alongside your metrics. Mistake 4. One size fits all. Different architectures need different schedules. What works for ResNet might not work for BERT. Let's wrap up. We've covered 7 powerful learning rate scheduling techniques. Step decay, simple and effective. Exponential decay, smooth transitions. Cosine annealing, natural curves. Warm restarts, escape local minima. Linear warm-up, stable initialization. Polynomial decay, fine control. One-cycle policy, fast training. Reduce on plateau, adaptive approach. Key takeaways. 1. Learning rate scheduling is not optional for competitive performance. 2. Start simple, then experiment with advanced techniques. 3. Always combine with proper monitoring and visualization. 4. Different problems need different approaches. If this video helped you, smash that like button, subscribe for more deep learning content, and let me know in the comments which scheduling technique you're most excited to try out.